All right, we're gonna continue our discussion of strain. Let's see, last time spent a lot of time talking about that. Started talking about steric strain. Um, and we came up with the fact that if you have a more complicated molecule than butane, you have to worry about conformations about multiple bonds, and that if you have a certain combination of gauche plus if you have the gauche plus gauche minus conformation, you actually put two methyl groups sort of bumping into each other. And I think we looked at that in Spartan, where this was the worst one. It's gauche here in a clockwise sense. The thing in the back is clockwise relative to the thing in the front. Then if we look down this bond, it's sort of gauche but counterclockwise. So that's a plus-minus combination. And again, it puts those two methyl groups pretty close to each other. And that can be a problem. So when dealing with chains, hydrocarbon chains, you don't necessarily want to believe that something like this is the low energy conformation, because it's not. Now, I don't know what good it does you to know that, other than be thinking about conformations, because two atoms, even though there are four bonds, well, one, two, three, yeah, four bonds apart, two groups could still bump into each other if the intervening atoms are are constrained. All right, so briefly, we talked about rotation around carbon-carbon bonds. There's a whole story to tell about peptides and proteins, which I will defer to another time, or perhaps never, but if you really want to know, you can come talk to me and I would be happy to talk for a couple hours about it. Nobody takes me up on that, and that's okay, I'm not offended. I want to talk briefly about something called allylic strain, because this, if any of you decide to work for Professor Castle, you're going to encounter this in one of his projects. So the idea with allylic strain, first of all, what does allylic mean? Anybody know?
Like, you know, like two double bonds, like close to each other.
Right, allyl does involve a double bond. Yep, totally.
But allylic strain,
So when you have a double bond, this position, one of the carbons, both of the carbons in that double bond are called vinyl carbons. And then the carbon adjacent to the vinyl carbon, adjacent to the double bond, is called the allyl carbon. And allylic strain involves the substituent on the allyl carbon. If it's something other than hydrogen, the following thing can happen. So suppose you've got this hydrocarbon chain, and you've got some non-hydrogen substituent attached to the allyl carbon. You now have an opportunity for those two groups to bump into each other. I'm sort of trying to represent weakly the van der Waals radius of hydrogen and then the van der Waals radius of this methyl group, to give an idea that these two groups can bump into each other. This is sometimes called A1,3 strain, A for allylic, and 1,3 for the fact that it's substituents on 1 and 3 that are causing the problem. Let's see. I don't know actually if Spartan has an example of this, but we can try. Double bond, methyl group. Okay, that'll be, oh, how about that? So from our perspective in that we were drawing, here is the double bond here's carbon 1, 2, and 3. Attached to carbon 3 is this methyl group. Allylic strain refers to potential clashes between this hydrogen and this substituent. And, you know, from this point of view, it doesn't totally look like they're touching each other, but if we look at space filling, you see that? It's actually touching pretty close. And if you were to rotate this methyl group, pretty soon this hydrogen would bump into that one. So that's a higher energy conformation, and it turns out that in order to avoid that, it'll twist itself so that the larger substituent on carbon 3 is now oriented away from the proton here. See that? So, and that's a difference that's worth about a kilocalorie per mole. It's kind of on the order of, I believe, a methyl gauche interaction. But if you you could imagine other things you could do to make this conformational difference larger. For example, if you put a substituent here, then you would have then the penalty for being in this conformation where the methyl group sort of eclipsed with the proton. Sorry, turning it this way. If we had some other substituent here, it would be even more sterically demanding, and that other conformation would be even more favorable. This shows up in the Castle Lab research where people are working on what are called dihydroamino acids. So if you look up, and they've published multiple times on this, but one of the leading references is in Orglet from 2017, Ancient History. Though I remember it like it was yesterday. And they're dealing with dihydroamino acids. So I'm going to show you just an amino acid. The squiggly line here represents that there's other stuff over here that we're not going to worry about. Here is the basic backbone structure of an amino acid. And again, the squiggly line means there's other stuff over here that we're not worrying about. This is the alpha carbon of the amino acid, and in typical amino acids, this has a hydrogen and then side chain. In the dihydroamino acids, you get rid of that hydrogen and you make a double bond between the alpha carbon and the beta carbon. And then you have a substituent here and a substituent here. This amino acid is called dihydrovaline, because it looks like the amino acid valine is the one where you have this isopropyl group going down. But if you get rid of this hydrogen and this hydrogen, and so that's an oxidation formally, you've got a double bond there. Right, so let's sort of see the situation that we've got here. And keep in mind, let's see, you've got a double bond, we'll call this 1, 2, and 3. And our double bond actually has a methyl group on it. And then this group over here is something that's not hydrogen, it's actually another carbonyl carbon. So you have strain between the substituent on carbon 1 of the double bond, which is this methyl group. That's bigger than we had over here on carbon 1. And then atom 3, which here happens to be a nitrogen, has a large group on it as well. And so you've got, again, A13 or allylic strain. And what this does is it significantly restricts the conformational freedom of this, of a dihydroamino acid. AA is for amino acid. So the Castle Lab has discovered that certain dihedral angles about this bond, and perhaps even this bond are favored because of that allylic strain. And they're starting to learn rules about where you can put these unnatural amino acids in existing protein and peptide secondary and tertiary structures, and whether that can increase their stability and resistance to proteolytic degradation. All right. Let's talk, anything you want to say about that? Let's talk about rings. And
What was the conformational freedom?
It restricts the conformational freedom of the amino acid, of the dihydroamino acid. Rotation around, I told you I wouldn't do this, rotation around this bond is given, the dihedral angle about this bond is given the Greek letter phi. The dihedral angle for rotation about this bond is given the Greek letter psi, and the rotation around this bond between carbonyl carbon and nitrogen is given the Greek letter omega. And having this A13 strain affects the values that the amino acid can adopt for these groups. All right, so rings. Of course, when we draw them from above, it looks like they are flat. So here's cyclobutane, and we can, if we assume that it's perfectly flat and we fill in all these carbon-hydrogen bonds, we've got a problem. The first problem is that if it's perfectly flat, the angle here has to be 90 degrees. And that's substantially different from what you expect in an sp3 hybridized atom. Now remember, even though we could go pure molecular orbital theory, our approach is going to be to still maintain focus on individual sigma bonds. We'll still use hybridization, but we'll remember that antibonding, empty antibonding orbitals are present, and we'll remember the idea of combining p orbitals together to make conjugated systems. So in this case, we've got pretty substantial angle strain, less than cyclopropane, but still pretty substantial angle strain. And then the other thing you've got is what some texts call torsional strain. So we're going to put our eye in the plane of the page and look down each of these. These are, whenever I draw something like this, you're just setting your eye in the plane of the page, and sometimes because I'm a nerd, I can't resist making those bloodshot evil Sith eyes. But anyway, we're looking down the carbon-carbon bond, and if it were totally flat, you would see that the hydrogens in the front are always eclipsed with the hydrogens in the back. And of course, this you'd expect to be unfavorable. So we call the fact that when the ring is flat, all of the CH bonds are eclipsed. That's going to cause what your text may call torsional strain. Torsion is another word for rotation around a bond. And it's sort of another word for dihedral angle. Okay, so what the ring will do is it's going to, of course, if you're cyclopropane, 3 points determine a plane, so there's nothing you can do. But if you have more than 3 points in your ring, you have the opportunity to distort from planarity to relax the angle strain. And so these rings will do something called pucker, where instead of being totally flat, what will happen is, how to best draw this? I'm not sure. I'm going to draw a four-membered ring in this sort of puckered conformation, but I'll just draw the hydrogens in the front. And you can see that this hydrogen is not eclipsed with that one, this hydrogen is not eclipsed with that one. So it's sort of, we move a couple of atoms up out of the plane, and that gives us a little bit of relief from angle strain and from torsional strain. And you can almost hear the ring relax and say, ah, when it does that. So let's just look at the puckering of cyclobutane. We'll draw a square, and it doesn't want to show us the totally flat conformation because it's too unstable. So let's just zoom in and look at that puckered conformation. This is the view that we took in the thing that I drew over in Notability. You've got the two carbons in the middle here and here, lifted up out of the plane of these two carbons. That relieves some of the angle strain. We could calculate this bond angle, but you can see it's greater than 90 degrees, so it's not as strained. Then if you look down one of these carbon-carbon bonds, you can see that the hydrogens are not eclipsed. They're not perfectly staggered, but this is as good as you can get. With the four-membered ring, it's, of course, you can imagine multiple puckered conformations. If I were to call each of these atoms, 1, 2, 3, and 4, I could imagine a conformation where 2 and 4 were down and 1 and 3 were up. But there's no energy difference whatsoever between those two, and it's easy to interconvert between them. And so people don't typically spend a lot of time worrying about cyclobutane rings, just the idea that they're pretty flexible. Meaning that you can flip back and forth between various puckered conformations. Okay, the options for a 5-membered ring are a little bit bigger. For example, so here's cyclopentane. If it were flat, it faces the same problems. You can, let's see, draw a couple of different puckered conformation. You could leave 4 of the atoms all in the same plane and then bring the 5th atom out of the plane. 1, 2, 3, 4, 5. This looks like a really bad chair. It's not, because there's not 6 atoms there. So yeah, you'd have 1, 2, 3, 4, and 5. 1, 2, 3, and 5 are all in the same plane, and 4 is lifted up out of the plane. That would mean that hydrogens on 1 and 2 are still eclipsed with each other, but that the hydrogens on carbon 4 are not eclipsed with the hydrogens on 5 and 3. This is called the envelope conformation, because if you sort of look at it, most of you probably haven't sent a letter very frequently in your lives. I don't know. I don't tend to do that anymore, maybe. I used to write letters to Amber while I was on my mission, so I did this a lot. But of course, an envelope looks like this, and you have a flap up here that you can close while your letter goes inside. And anyway, some people thought that this sort of looks like that. Right. The other option is what they call a half chair. And in the half chair, there's a couple of atoms out of plane. So the half chair is going to look like this. In the half chair, you have, and let me just sort of, I'll fill in hydrogens. It starts to look a little bit more like a chair. I won't fill the hydrogens in the back very well. but you've got these three atoms, 1, 2, and 3, all in the same plane. And then you have these two atoms out of plane. And we can look at the half chair. I'm not sure Spartan will give us the envelope confirmation. It may just give us the, dang it. Oh, hold on. May just give us, yeah. So Spartan's going to show us the half chair confirmation. You can see that if you sort of look at it from this perspective, you've got the 3 atoms in the back here that sort of occupy the same plane. And if you look at those 3 atoms, they are pretty close to eclipsed with each other, the CH bonds. And then in the front, you have 2 atoms, one's above the plane and one's below the plane. And so the question is, you've now got a lot of different combinations, because what if, a lot of different possibilities, like what if this atom was up and that one was down? Well, that's an option. What if you moved it one over, so the other 3 atoms were in the plane and then this one was up and the other was down? So it's thought that in a lot of cases, cyclopentane rings vary who gets puckered where, and so there may be a lot of conformational diversity. The place you will see cyclopentane rings the most will be, at least in terms of biology, will be in the amino acid proline. I'll draw what it would be like in a protein. So this is the amino acid proline, and then carbohydrates, for example, the ribose ring of a ribonucleotide. Sure, why not? And then we'll put, ooh, can I draw the structure of, nope. Let's see if I can draw the structure of some. I believe that's guanine. In any case, this ring is a 5-membered ring, and there are, because you've got these large groups, and in an oligonucleotide, this at least is strung together with some other. This is strung together with another carbohydrate here, and this has another phosphate group here. There are preferred conformations about that ring, and you can study it if you want. I heard a talk about it once, and my eyes sort of glazed over, so we'll move on from that, unless you have questions or anything you want to know. Sure.
In proline, which carbons are going to be put on a plane in that half-chair conformation? Since it's probably not the N and the alpha carbons, since they're locked.
Right. It's a good question. It's typically, I mean, there's a few different options, but the puckering for proline usually happens out here with either these 2 or these 2. And there's another interesting story with proline that we're going to come back to. Others? Okay, cyclohexane, we're really not going to spend a huge amount of time on, because I presume that you're basically familiar with that. Everybody's okay with cyclohexane? Okay. So here is chair cyclohexane. 6-membered rings like this are lovely in organic chemistry, because if you look at the bond angles in cyclohexane, they're almost exactly tetrahedral. So you're able to adopt a structure that has no angle strain anymore. And it basically also has no torsional strain, because if you look down all those carbon-carbon bonds, everything is staggered. Okay? What else to say about that? It's going to show us a higher energy conformation, and this is, I'm going to get it wrong. This is called the twist boat. And you may have had somebody tell you before that cyclohexane chairs are in equilibrium with a high energy conformation. So here's one of the chairs, and then they tell you, well, the high energy conformation is like this, and you have these two hydrogens that bump into each other. Does that sound familiar? Have you heard that before? It turns out that this is not an intermediate. It is a transition state. So it's not correct at all to say that the chair is in equilibrium with the boat. It turns out if you take the boat and distort it a little bit, that is, take either carbon here and here that have the hydrogens and twist them away from each other, that's the twist boat. So I'll show you, let's see, an energy diagram. Nope, that wasn't it. Sorry. Sure. Let's see if I can show you. That was also not it. See if I can show you a free energy diagram for cyclohexane. Aren't you glad I didn't do any of that? Still no, huh? Dang it. Oh, there it is. Okay, so you have a chair. If you take this carbon here and pull it upward, you go through a transition state called a half chair. It's like the, it's kind of like the cyclopentane half chair in the sense that these atoms are sort of now all in the same plane. And then you can drop down into the twist boat. The boat is a higher energy conformation where all of these bonds are eclipsed with each other, and these two substituents are pointing directly into each other. That's 1 or 2 kilocalories per mole higher than the twist boat, and you can go over one boat to the twist boat and then back over this barrier to get to the chair. Right. Anything else we want to say about that? Let's talk substituted cyclohexanes. I've got some tables here, but we may be able to see some data on Spartan. So let's just put a methyl group here. Ah, good. Okay. So you can see here that the methyl group adopts, is at an equatorial position, right? Notice, and it doesn't matter because there's no stereochemistry to consider here, but notice that that equatorial methyl group is angled downward, and it's on a carbon that's sort of upward in our chair. You have 3 carbons, 1, 3, and 5 that are sort of upward, and then you have 2, 4, and 6 that are downward. And the downward position on an up carbon is equatorial. If we go up by about 1.7 kilocalories per mole, we can chair flip. Now the carbon that has the methyl group, you can see, is no longer at an up sort of position. It's now angled downward. And the methyl group that was angled downward but equatorial is now still down but axial. Familiar with that? Yeah. Now there's an energy difference between those two. It's 1.7 kilocalories per mole worse to have the methyl group axial. And the reason for this is steric clashing between these hydrogens that are axial and the axial methyl group. And these hydrogens are each 1, 2, 3 atoms away from this substituent. So the hydrogens on, oh, dang it, I really did try to stop that. I don't know what to do about that. It goes to sleep every time. Right. So carbon 1, carbon 2, carbon 3, so you have what's called a 1,3 diaxial interaction between this hydrogen and this methyl group, and you've got another one there. Another reason that the axial conformation is less favored is because now you have a gauche interaction of that substituent with the ring. So you got two sort of things going on. If we look at a space filling model, you will see that actually that methyl group is bumping into those hydrogens at those 1, 3, and I guess 1, 5, or we could still call this 1, 3. And in fact, the methyl group does have a preferred conformation. You'd like to have this hydrogen splitting the difference between these two. The equilibrium between axial versus equatorial can provide a measure for how stable, or rather how large a group is, right? Because for just regular cyclohexane, there is no free energy difference between the two chairs, right? You've got one chair here and the other chair there. If, however, you break the symmetry and you put a substituent here, when it goes to the other chair, it's going to be high. It's going to be axial now, and that's going to push this chair higher in energy by a certain amount. And what we just looked at in Spartan tells us that that's going to, if you have the methyl group, that's going to increase by about 1.7 kilocalories per mole. So, and we can just do a few perhaps other examples. Let's change that to, say, an OH group. We'll look at the structure there. We've got axial, or sorry, an equatorial OH group. There's a couple of other conformations that are going to vary in what's going on with the OH proton. We're going to ignore those. But what you've got here is a conformation where the OH group is down equatorial, and then here, less than a kilocalorie per mole higher, you've got, well, and it depends on whether you're comparing apples to apples, because it does actually matter where that OH group is. But anyway, if you're given the option of rotating around, we can't quite see it. If you're given the option of rotating around this carbon-oxygen bond to get this proton out of the way, then the difference between the two chairs is less than a kilocalorie per mole if axial versus equatorial, though I suppose this comparison, which is more like the comparison with the methyl group, where the proton is actually sticking into those 1,3 diaxial interactions, is about a kcal per mole higher in energy. And you can go through and do this with all kinds of substituents. Let's say fluoro. Turns out that if you look at the space filling model, fluoro is not that much bigger than hydrogen. So the difference between axial and equatorial fluoro is actually not that great. And in fact, this is telling you that it's actually better to have the fluoro axial. That's an interesting result, which we would need to talk about in a little bit. Similarly, we could go back and replace fluoro with chloro. And notice that the carbon chloride bond is longer than the carbon fluoride bond. Right, so you can take the free energy difference. Nope. For any given substituent, you can take the free energy difference between having a group equatorial versus axial, and you can measure how upward in free energy it is. And you can measure the delta G of that reaction. If, for example, R equals the methyl group, the delta G for that reaction is 1.7 kilocalories per mole. And there are lots of values for other types of substituents. For example, the OH group, depending on its particular shape, was in the range of 0.6 to about 1 kilocalories per mole. It turns out that if you put a methyl group on that oxygen to make an ether, the numbers don't change a lot, and the reason for that is that you remember that in the OH group, we have a conformation where we can move the hydrogen out and away from the other axial substituents. Similarly, if we put the methyl group there, it doesn't really interfere with the other axial substituents. So the free energy is about the same. Other groups that you might be interested in, let's see, an ethyl group, for the same reason, if R is CH2, CH3, it doesn't really increase the delta G value for going axial very much over just the methyl group. And that's again because you can rotate around a carbon-carbon bond such that this methyl group is out of the way and doesn't interact with or impact those axial substituents. It gets a little bit crazier when the squiggly line indicates that this R group is attached to something. If you add another methyl group and get to isopropyl, of course the A value goes to, or the delta G value goes to 2.2 kilocalories per mole. It's a little bit bigger than for the ethyl group, and that's because you now have more methyl groups present. The T-butyl group famously has a delta G of 5, so that the conformation around 5 kilocalories per mole, so that the conformation is basically inaccessible. These kinds of numbers are where it's useful to know what I told you about room temperature. 1.4 is about a factor of 10 in equilibrium constant. So you'd expect the ratio of axial to equatorial, or rather equatorial to axial, to be somewhat lower than 10 to 1, right? Somewhere, and we could calculate what that number is. It's not 1 to 1. If it were 1 to 1, delta G would be 0, but it's somewhere between 1 to 1 and 10 to 1. In contrast, the methyl group, it would be about 10 to 1, even a little bit greater than that, axial versus equatorial, and so on. Of course, if it's 5, you've now got multiple orders of magnitude, so we're looking at 1,000 or 10,000 to 1. Go ahead.
How do these relate to like A values and stuff?
Right, these are, you've heard of A values before. These delta G values are called A values, presumably because they're about something being axial instead of equatorial. And we will use A values as a measure of size of groups. So you will hear chemists basically rank substituents in steric size based on what they've learned from A values. And so you have to remember that those values come from a cyclohexane conformational equilibrium, which may not capture all the features of whatever system you're trying to apply it to. But you can use these A values to predict, if you have two substituents, which one do you want to be axial versus equatorial. You can also, there's an interesting story from the mid-90s where chemist Eric Anslin, you don't necessarily care about the reference, but I'm just putting it here to let you know that this is real, did an experiment where he took a cyclohexane ring. It really shouldn't be doing that because it's plugged in. Oh well. I'll see what I can learn. He took a cyclohexane ring that had an isopropyl group on it, but when the isopropyl group was equatorial, the two OH groups would need to be axial. And then you could switch to a different chair. You could go to the other chair. This up equatorial isopropyl group would become up axial, whereas the two axial OH groups, this one was up, it's going to still be up, but at an equatorial position, and this one will be down at an equatorial position. And Anslin reasoned that there might be a hydrogen bond between this oxygen and that hydrogen. And if so, you could predict what this delta G would be based on A values alone. So you could predict that, okay, this is going to be the A value for having the isopropyl group axial minus the A value for having one OH group axial minus the A value for having another OH group axial. In other words, I get these numbers back when I go from axial to equatorial. And then I lose, I lose some stability when this goes from equatorial to axial. So you measure the actual number and, yes?
Are you adding the A value for the OH on the axial from the left side?
What I'm trying to do is predict the difference in free energy between this conformation and this conformation.
Yeah.
So,
That's, yeah. So
yeah.
I think you're supposed to like add up the axial value for the OH
Yes.
there and then subtract from this one, right?
No, because the A value is a free energy difference, and so it refers to a change. So the A value that applies, for example, for isopropyl is for going from equatorial to axial. So for that process, we are going to use the A value because that's uphill in energy. We go from having something axial to something equatorial. That's going to be downhill in energy, which is why we subtract the A values. So no, you don't add up all the A values. I suppose you could. If you wanted to, you could say, okay, there's no A value here because it's equatorial. You could use the A value here and the A value there. And then I suppose you could use the A value for the isopropyl group and put 0 here. Then calculating the free energy difference, it would be products minus reactants, and you would get to that equation. Yep. So that's a great way to think about it. Sorry about that. It took me a while to get there. So he measured this free energy difference, and it was bigger than expected because of this hydrogen bond. So if you take the measured free energy minus delta G that was predicted, whatever's left, he reasoned, has to be a free energy due to a hydrogen bond. And people have been interested in measuring strength of hydrogen bonds for like a long time. This was an early way to do it. There's a lot more ways to do it, which we can talk about another time. Right. Hold on, let me see what time it is because I can't ever tell. All right, I've got about 4 minutes. There's some stuff in your text about larger rings and transannular interactions. It's worth looking at just to be aware of and know where it is to come back to it. In general, realize that rings in the size of, say, 5 to 7 are going to be considered relatively strain-free, whereas rings smaller are going to be considered highly strained. And then in the interval from like 8 to 11 membered rings, you've got strain again, because groups across the ring start bumping into each other. Larger rings beyond that involve minimal strain. Okay. And there's more we could say about other stuff, but I think we need to sort of stop there. So I want to talk now, and we'll have to stay on chapter 2 a little bit next time, about something that's called stereoelectronic effects. In this chapter, we're basically talking about things that can affect the shapes of and stabilities of organic molecules. And one reason for why an organic molecule might adopt a particular shape is sterics, to avoid clashes. The other reason is stereoelectronic effects. And people will say, you may have heard this before, if not, you surely will over the course of your grad school career. If it's not sterics, it's electronics. Those are the two explanations for anything. So if somebody asks you why in some group meeting and you say one of those two things, you're going to be on the right track, though you should still think about it before you say something. So what do we mean by stereoelectronic effects? Well, let's start with something that's called the gauche effect. And this is kind of an interesting story. We're used to thinking of, let's just go 1,2-difluoroethane. Okay. It could exist in this conformation in which the fluoro groups are anti to each other. Or it can exist in this conformation where the fluoro groups are gauche to each other, and in the Newman projection we're looking down the bond from that direction. So fluoro group pointing straight up in the front, and on the back we've got it angled out to the right. Now, based on steric arguments alone, you would say that this anti-conformation is more stable than the gauche conformation, but it turns out the gauche conformation is preferred. All right. That's weird. What on earth is going on there? And the answer has to do with orbitals and hyperconjugation. All right? So consider first the difference between carbon-hydrogen and a carbon-fluorine bond. Here's carbon, here's hydrogen, roughly the same energy. Where should fluorine be? Should it be higher or lower in energy than hydrogen? Lower, because of increased electronegativity, right? So a carbon-fluorine bond will be more stable than a carbon-hydrogen bond. All right? But this effect will also lower the free energy of the antibonding orbitals. So the carbon-hydrogen sigma star is higher in energy than the carbon fluoride sigma star. Okay? So that's, you've got to understand that before you can understand the gauche effect. But the basic idea is you want the CH bonds, which are higher in energy than CF bonds, to overlap with the CF sigma stars, that creates a better hyperconjugation interaction. That was fast. We'll go through it a little bit more slowly next time so you can get it. But that's a famous effect that you will see in various places. Have a good weekend. Enjoy conference. Your exams are due, I said Monday, right? End of the day, and I'm not actually going to check at 5, so
Till midnight.
knock yourselves out.
Okay.
Heck, as long as you get it to my office before I come in on Tuesday at an undisclosed time, you're fine.